When an AI freezes on a logic puzzle it solved just moments before, we are seeing cognitive load in action. It is the digital equivalent of an engine trying to process a dense, convoluted encyclopedia, buckling under the physical weight of the vocabulary. This struggle creates a massive engineering bottleneck. Every extra microsecond a system spends decoding obscure words burns through server power and drives up compute costs across the entire pipeline. A strange logic gap exists here. Giving a large language model two prompts with the exact same meaning often produces wildly different results based strictly on word choice. A math problem written with rare academic jargon often triggers hallucinations. That identical problem, translated into common language, is executed perfectly. We are suffocating these models with unnecessary linguistic weight. A surplus of complex vocabulary creates a greater drag on efficiency than any lack of raw hardware. To solve this vocabulary overload, researchers formalized a principle called Adam's Law, the Textual Frequency Law. The logic follows the model's pre-training. Because these systems see common, high-frequency words billions of times more often than rare ones, they find simple data significantly easier to process. This diagram shows the solution. Passing a prompt through a rephrasing loop ensures high-frequency language, making token prediction mathematically easier. The accuracy frequency curve confirms this. As word frequency increases, accuracy follows a sharp upward trajectory. Selecting common expressions strips away error-causing low-frequency noise. Applying Adam's Law allows for an immediate boost in reasoning accuracy by speaking to the AI in its preferred high-probability language. However, most frontier models are closed source. Without access to the original training data, engineers cannot see which specific words a model considers frequent. To bridge this gap, engineers use a workaround called Textual Frequency Distillation, or TFD. During TFD, we force the AI to perform story completion tasks. By observing the model's natural word choices, we can map its internal frequency weights and identify its linguistic comfort zone. This acts as a diagnostic practice test. It lets us build an accurate frequency dictionary while the model's internal architecture remains completely obscured. Once the AI's vocabulary preferences are mapped, we move to deployment through curriculum textual frequency training. Rather than fine-tuning with randomized data, this pipeline organizes training examples in a strict increasing order of sentence-level frequency. This sequential approach builds foundational confidence on high-probability language before the model is introduced to complex low-frequency edge cases. Ordering training data this way replaces chaotic, compute-heavy workloads with a streamlined path toward model mastery. To validate these mechanics, researchers tested the framework against standard industry baselines using the textual frequency paired dataset. High-frequency prompts triggered an immediate performance spike in math reasoning, helping models navigate complex logic with far fewer errors. This cluster of radar charts shows the impact on machine translation across 100 different languages. The expanded shaded regions represent the high-frequency partition, which consistently outperforms standard baselines across the entire global set. We also see distinct improvements in agentic tool calling. The AI becomes more reliable at executing software actions, proving that frequency logic applies to more than just text generation. Adam's Law functions as a fundamental lever, elevating baseline intelligence across a wide spectrum of critical enterprise tasks. There are technical trade-offs. Mapping frequency via distillation requires a significant upfront compute investment that engineers must factor into their development budgets. Furthermore, simplifying vocabulary only reveals a model's existing potential. It cannot provide context or reasoning skills that were missing from the pre-training. When the vocabulary is optimized, however, the resistance disappears. The system processes complex data streams with total fluidity. This shifts the focus of data engineering. Instead of just scaling compute, we have to consider if we are speaking the AI's language. Share your thoughts on frequency-based filtering in the comments.